In the name of Almighty God, I am Master Hassan Kosha, and today I want to talk about introduction to pipe flow module. The pipe flow module is an optional add-on package for computer multiphysics designed to model and simulate fluid flow, heat, and mass transfer in pipes and channels. Compressible hydraulic transient and acoustic waves can also be modeled using the water hammer interface and pipe acoustic interface, respectively, to analyze the stresses and deformation in the pipes. The pipe mechanics interface is available. The pipe flow module can address problems involving flow velocity, pressure, temperature, stress deformation, and sound waves in pipes and channels. Modeling pipes as curves in two-dimension or three-dimension gives a great advantage in computational efficiency over meshing and computing three-dimensional pipes with finished diameter. Figure 1 illustrates the pipe flow interface reduces the three-dimensional flow problem to a two-dimensional or three-dimensional curve. Pipe systems for the which the ratio length diameter is large enough that the flow inside of each pipe segment can be considered fully developed or suitable for the pipe flow module. The physics interfaces in the module define the conservation of momentum, energy, and mass of fluid inside a pipe or channel. The flow rate, pressure, temperature, and concentration fields are modeled as cross-sectional average quantities so that they only vary along the length of the pipes. The pressure losses along the length of a pipe or in a pipe component are described using friction factors. A broad range of built-in expressions for Darcy and Fanning friction factors cover the entire fluid regime from laminar to turbulent fluid, Newtonian and non-Newtonian fluids, different cross-sectional geometries, and a wide range of relative surface roughness value in addition to the continuous friction or pressure drop. A long pipe stretch, the pressure drops due to the irreversible losses in components such as bands, contractions, expansions, T-junctions, Y-junctions, and valves are computed through an extensive library of the industry standard loss coefficients. Pumps are also available as flow-inducing devices. The features in this module are intended for modeling and simulating compressible and weakly compressible fluid flow in pipes and channel systems, as well as compressible hydraulic transient and acoustic waves. Typically, simulations yield the velocity, pressure variation, and temperature in the systems of pipes and channel. Hydraulic transients are also possible to model. These can be the result of valve that is closed rapidly in a pipe network, which is referred to as a water hammer. The pipe mechanics interface is intended for modeling a cylinder pipe with arbitrary cross sections. Among the computed results are displacement, rotations, stresses, strains, and section factor forces. Now I want to go to the applications. The module can be used to design optimize complex cooling systems in turbines, analyze a ventilation system in building, pipe systems in the chemical process industry, and pipelines in the oil and gas industry, just to mention a few applications. Figure 2 illustrates a probe tube microphone model using the pipe acoustic transient interface in the pipe flow module. Any devices in which you find flow waves or mass or heat transfer phenomena in narrow pipes or ducts are candidates for simulation with the pipe flow module. Classical pressure drop and mass flow calculations through piping which bands, valves, tanks, and so forth are well suited for the pipe flow module. Figure 3 illustrates tutorial model describing the discharging of a water tank to a simple pipe system with bands and valves. For heat transfer studies, the pipe flow module includes several automatic couplings to the surrounding heat sinks or sources, both shortcut methods with semi-empirical correlations for force and convection, and also direct coupling to three-dimensional solid in which the pipe is embedded. Figure 4 illustrates methods for heat transfer to the surrounding from the left to the right: forced convection, natural convection, and also solid geometry. An example of an application which demonstrates the capabilities of pipe solid coupling is a mold coupling model in the pipe fluid application library. When manufacturing devices in polymeric materials, the structural integrity of the end products is very sensitive to the cooling history in the model. Figure 5 shows the heat transfer to the cooling channels embedded in a cooling model is simulated to understand the control cooling of a polyton steering wheel. A non-thermal pipe fluid interface is used in the model. So thank you so much for watching my tutorial video until the end. Today is 22nd of the May 2026. Time is 4:42 p.m. Also, you can download the proper and appropriate computer physics software file from my github.com/maxwellscript.